Logan Calc BC, and I'm going to try a little something different this time, and I'm going to record the video over here at the Promethean board. For one, I find my writing is a little bit neater, and for two, I think for this one, some of the equations and stuff that we're going to be writing out might be better if we see them up here. So I'm going to try that for this part of the video, and hopefully this will work out a little bit better. The idea today is, of course, that we are now moving from just talking about power series to actually doing some calculus with power series. That means differentiating and integrating. And so we'll start by looking at the derivative and the integral and what that looks like in a power series. And then we're going to look at some of the ramifications that the calculus has on the integral of convergence. And so let's go ahead and get a power series on the board here so that we can take a look and see just how that might be impacting our function. So the first thing I want to do is just talk about deriving them. And so if I have a power series, what does it look like if I wanted to take a derivative? So let's just have a, I guess we should title this. This is the calculus of power series. And actually, while I think of it, I'm going to put the microphone on just because I think that helps with the audio on the recording. So I'm going to just give us a generic power series. So it's going to be a to the n, and it's going to be x minus c to the nth power. So here we go, a sub n, x minus c to the nth power. And so this is just your basic power series. I don't know what the formula for a sub n is. I don't know what c is. I just know that it's a power series because it's got this variable x and we're raising it to a power here. So if I want to think of calculus then, okay, so when I'm taking a derivative, for example, what do? Right? Well, we bring down the power and we subtract 1 from the power. So if this is the function f of x, and it's represented by this power series, then what does its derivative look like? Okay, so the derivative, come on, one more. Well, that's f prime of x. And literally, because it's the derivative with respect to x, okay, n is just part of the series. We just keep the series. Now, I want to be clear here. I'm going to change from 0 to 1. Okay, and so, oops, I just said it, I was going to do it, and I didn't write the right thing. Why do we change from 0 to 1? Because that first term is a constant here, and so that term's going to drop off. If n was 0, we would just have a sub 0. We would have x minus c to the 0 power. So there would be no x. And the derivative of that constant would be 0. So I'm actually going to start my derivative summation at 1. Okay? Now, a sub n is still going to be there. That's a constant. It's dependent upon n. It's not part of the derivative. Okay? And so then we just use the power rule. N x minus c to the n minus 1. And that's what you do to take a derivative for a power series. Now, before we get too far into this, let's just write out a couple of terms of the two series, and I think you'll see pretty clearly how this plays out. So if I had written out the terms, why did that not change colors? It's supposed to change colors. I'd have a0, there we go, plus a1 x minus c to the first, plus a2 x minus c to the second, plus a3 x minus c to the third, and so on. Okay, so if I were to think about calculus in terms of deriving each one of those terms, well, check it out. We get the same kind of thing in here. You know, if n is 1, okay, we get a1, and this is 1 times x minus c to the 0, we get a1. Okay. If n is 2, we get a2 times 2 x minus c to the first. If n is 3, right, we get a3 times 3 x minus c squared. And so on. I want you to think about, though, in calculus, what would happen to a1 if we took its derivative? It would, or sorry, a0. It's a constant. It would be 0. a1 x minus c to the first power, right? That would just be a1. a2 x minus c squared, when we bring down the 2, we get 2ac. You can see how it's not really all that surprising, okay, that these are the terms of the series, based on the fact that I just used the power rule inside the summation. It yields the same series as if we were to take the derivative of everything on this side. So that's taking a derivative for our power series. Okay, and obviously these are infinite, so they go on and on and on, on and on. All right. What about integrating? Well, as you can imagine, because these are really just big polynomials, we just integrate each term separately. We use the power rule again. So I'm going to go to the next slide here. And this time I'm going to integrate f of x. Okay. And now, don't forget, right, there's a c involved here. Yeah. There's going to be some constant of integration plus then our summation. Now, our summation isn't going to be, what happened? Oh, there we go. Any big surprise here. A sub n is still going to be present, of course. And then when we use the power rule for integration, we add 1 to the power. And we divide by that new power. And that's how we integrate a power series. Okay. Thinking about then, my original power series that I had, right? I would integrate each one of those terms, and you would see that this is exactly what we would get. If I start with, if n is 0, right? Well, then we get a0, but now we get it multiplied by x minus c to the first power over what? Plus, then if n is 1, I get come on, where are you, ink? a1, there we go, x minus c to the second power over 2, right? And then for the third one, right, when n is 2, we get x minus c to the 2 plus 1 over 3, and so on and so forth. And it just continues on, which is exactly what we would have gotten had we integrated each one of those terms. So I don't think it's particularly surprising that this is how this works, because I think we're pretty accustomed to the power rules as they are written for our functions when we had them before. Putting them in series form doesn't really change the nature of the rules. It does have this weird summation part to it, but other than that, we're keeping in mind that the summation is dealing with n. The function is a function of x, so n doesn't really play a big role here. It's just a shorthand way to write it. It doesn't get, until we start talking about convergence and divergence, do we have to worry about the fact that it is a series. Okay, so let me do an example with an actual function here so that we can kind of get a feel for it. And then we'll take a look at some of the ramifications that the calculus has for the radius and interval of convergence. So let's see, our first example here. So this will be our example number 1 for today. Example 1. There we go. So I'm gonna use the sum 0 to infinity, and I'm gonna have x to the n over n factorial. There we go. And so when I take the terms of this function, let's say, Okay, so like if n was 0, right, we'd have x to the 0 over 0 factorial, right? That's just 1. Okay, and if x is 1, that's supposed to be a plus sign. If n is 1, we have x over 1 factorial. And if n is 2, we have x squared over 2 factorial. And if n is 3, we have x3 over 3 factorial, which is really 6. And if n is 4, we have x to the 4th over 4 factorial, which is really 24, so on and so forth. Okay. If I take the derivative of that, okay, so what would the derivative of this look like? Well, you know, if I just write out the term, the derivative of 1 would be 0. The derivative of x would be 1. The derivative of the x squared term, I bring down the 2. The 2 would cancel the 2 in the denominator, right? It would cancel, so we just have an x, right? If you bring the 3 down here, 3x squared over 3 factorial, well, 3 factorial is 6, so when you cancel that out, you get a 2 down here. And you might be seeing what's going to happen here. We're going to get x cubed, and the 4 would cancel, but we'd have the remaining stuff for 3 factorial, and so on and so forth. And lo and behold, look at the series that we have now. Look familiar? It's the same series we started with, right? Yeah. Oh, what function is it that we know derivative is the same as the original function? Yeah, that is the power series for e to the x, right? We used it before. We used it a couple days ago. And it's still true. Yeah, this is still e to the x. And when you derive e to the x, what do you get? You get e to the x. And look, the power series are identical. The function and its derivative are identical. So kind of a cool thing in power series, that everything that we would expect to have played out from our earlier calculus, that's still going to work out. Okay, we could do the same thing with the integral, of course. There'd be the c in front, but we would still get the same exact function, e to the x. Okay, enough playing around with that stuff. Let's get to the real meat of the story here. The actual convergence of the series. Okay, now if it's point convergence, if it's just a single point, if the radius of convergence is 0, okay, then deriving and integrating, it's not going to change that. Okay, it will still only converge at its center. If you're worried about infinite convergence, okay, so they will converge for all x as well. Where we start to see some interesting things occur is with the finite interval, where the radius is just equal to some number. Okay, and specifically out at the endpoints, some stuff starts to change if we integrate or differentiate. Okay, and so usually there's this actually in the book, Dr. Larson actually buries it at the bottom of a page. I can't remember the page number, I think. Hang on. It's the bottom of 622. Okay, there's this a little note down there. It's actually a theorem in a lot of books that says if the derivative has convergence at the endpoints, then the original function has convergence at the endpoints. But that's not necessarily true the other way around. Okay, if the function itself converges at the endpoints of the interval, it does not necessarily mean the derivative will too. So we want to check. In other words, we need to check the radius of convergence and the interval of convergence for the derivative of the integral because it could be different than the original function. And so with that, we will head to example number 2. And example number 2's series is x to the n over n. Okay, so we actually have seen this one before. Okay, we looked at the convergence of this particular function before. we know that the radius of convergence for this was 1. We actually showed that it converges at the lower limit of -1, but not at the upper limit of +1. Because remember, it was at +1, it's the harmonic 1 over x. I'm sorry, 1 over n. And at the negative, it's -1 over n, and the -1 over n converges. If that doesn't sound familiar, check out the previous video. It is one of the series that we proved in the previous video. Use the ratio test, and we established that the radius was 1. So for f of x, we know that the radius of convergence is 1. The interval looks like this. Okay, so radius of convergence here, and the interval here. It's hard to pick up the pen over there. There we go. Okay. The radius of convergence of the interval of convergence is right there. That's true for f of x. Okay. So let's take a look and see what happens when I take a derivative and what happens when I take an integral. So first of all, let's grab a different color so that we're clear here. Let's start by integrating. There we go. The integral of f of x dx. Okay, well, I know that when I integrate it, right, I get c plus the sum, n equals 1 to infinity. Okay, so there's still going to be a 1 over n in here. Okay. I know I'm going to add 1 to the power. And I'm going to divide by that new power here. Okay, and much like we did before, I'm not so concerned about the constant when I'm talking about convergence, because that's just a constant. I need to know what happens in terms of convergence of this new series here. Okay, and let's use the same thing we've been doing from the previous one. Let's use the ratio test. Let's look at the radius of convergence. And then let's look at the interval of convergence for this new series here. So I'm going to set up my ratio test. There we go. And I'm going to add 1. So it's going to be x to the n plus 2, okay, over n plus 1 times n plus 2. And I'm dividing, but I'm multiplying by reciprocal, so you know the drill. Okay, and there's some cross-canceling that will happen here. The n plus 1s are going to cancel. Similarly, x to the n plus 2, x to the n plus 1, they're different by 1 factor of x, right? So these will all cancel out all of those, and it'll be x to the first. And so we're left with something I think you'll recognize. That is the limit as n approaches infinity of x times n over n plus 2. And when you look at the convergence for that, you can take the x out. N approaches infinity of n over n plus 2. Oops. Oh, come on. There we go. And notice that that limit over there is actually 1. So the final answer here for the ratio test is absolute value of x. Because the limit of n over n plus 2 is in fact 1. So how will we know if this converges then? Well, if the limit for the whole ratio is less than 1. And so we have the same radius of convergence as the original function. Haha, coincidence? I think not. Okay, now the bigger question is, what is going on with endpoint convergence here? Okay, because through the process of calculus, we may change the convergence out at the endpoints. Okay, will the interval change? Maybe not. It doesn't. The radius won't change, but the interval could. So let's go back and take a look at our function. What happens if I put -1 in there? It's still an alternating series, right? If we replace this here, x here, with a -1 at the left endpoint, okay? Give it a second to catch up with us. There we go. A little too fast for it sometimes. Okay, -1 to the n plus 1 over n times n plus 1. Okay, that's still going to be an alternating series. So we just have to prove two things. Okay, what do we have to prove? Well, we have to prove that the limit as n goes to infinity of 1 over n times n plus 1 is 0. Well, yeah, definitely. That's 1 divided by infinity, for sure going to be 0. And we have to prove that a sub n plus 1 is less than or equal to a sub n. It's supposed to be equal to 1. There we go. Well, if I add 1, right, I get n plus 1 times n plus 2 in the denominator. And that is definitely less than 1 over n times n plus 1. Once n gets past 1. So, yeah, this is a convergent alternating series. Okay, what about the other endpoint? What if x is positive 1? Let's go to a different color. What do we think? Convergent or divergent in this case? Right? Changed, didn't it? Yeah, because look, this is 1 over n squared plus n. Okay. How could you prove convergence or divergence with that? 1 over n squared plus n might be a good one to do a direct comparison with, right? Isn't 1 over n squared plus n always less than or equal to 1 over n squared? It is. So by direct comparison to 1 over n squared, we know it's convergent. Why? Because 1 over n squared is a convergent p-series. Come on. So this series converges by direct comparison to 1 over n squared. Okay, so wow, the integral actually has a different interval of convergence, doesn't it? Because we just proved convergence at the lower endpoint of -1 and at the upper endpoint of +1. So let's back up. Let's back up. There we go. Okay. So while my original function had an interval of -1 closed to +1 open, my integral has a different interval of convergence. We've included now the upper endpoint, right? So the radius of convergence is still 1. What's this? It's just, yeah. So integral of f of x dx equal to c plus summation n equals 1 to infinity x to the n plus 1 over n times n plus 1. The radius is still 1, but this is now.
Attention please, there has been a report of an emergency. Proceed calmly to the nearest exit and leave the building immediately. Do not use the elevator.
All right.
Use stairwells where necessary. All handicapped
We have an alarm going off
shall
right
use
now,
the
so
building evacuation plan.
I'm going to have to pause the recording and evacuate the building, I think. So I'll pick this up as soon as I get back in the building. Thanks, guys. Thanks for your patience, although I know it's going to be
There has been
instantaneous
a
for you.
report of an emergency.
All right, guys. Well, I know that was pretty quick for you, but for us, it's been a little while here in the building. So there was a fire alarm that went off. It actually was related to some sort of a burning of something down in a kitchen somewhere. So we're back, though. We're back and we're ready to keep going. So yeah, I'd say thank you for your patience, but really you just saw like 10 seconds of me talking about it. That's about it. We were talking about this function here. Actually, let me back up. We were talking about this guy back here. Our function f of x was x to the n over n from 1 to infinity. And we took a look already at what happens when we integrate that function and how it had an impact on the interval of convergence. In the case of this particular function, it added in that it would be convergent at the upper endpoint as well as the lower endpoint. The radius of convergence stayed the same, okay? And I think you're going to see that that's pretty consistently what happens. The radius of convergence doesn't really change. The interval, though, will change, and the changes are specific to the endpoint. So let's move on, and let's talk about what happens when we derive this function. So same function. F of x is still represented by our power series of n equals 1 to infinity of x to the n over n. And now we're going to take a look at what happens when we derive this function. And so for the derivative of f, let's see, different color. Sure. How about green? Well, you can already see what's going to happen here. I'm going to be bringing down the power n, and that's going to cancel out the power in front. Okay. And so the n would come down and go over the other n, and we get x to the n minus 1. Now, in this particular case, whereas my first example, when I took the derivative, right, I changed the lower index number to go from 0 to 1. And that was because the first term was a constant. And when I took the derivative, that constant would have derived to 0. Notice, however, for our function this time, the red series, when n is equal to 1, it's actually still got an x in it. And so I'm going to go ahead and continue to use n equals 1 for the lower limit, because what was a linear term for the leading term, right? If n is 1, we have x to the first power. Now in the derivative, we should get positive 1, okay, when x is 1. And so I can leave starting at 1. So you do have to pay some attention to that first term. If your first term turns out like it was a constant and you don't change it, then what's going to end up happening is you're going to have like a term that's going to have a negative power in it or something like that, which is incorrect. So it's something to be aware of as you start getting more comfortable with the derivatives. You'll get the hang of it. Really, just take a look at the first term. If it's a constant, that term needs to drop out. So start the index 1 up from there. If it starts out and it's an x to a power, then go ahead and leave the power alone, the lower index value alone. These cancel, and I'm simply left with x to the n minus 1. And so when we start considering the radius of convergence and the interval of convergence for this, notice that again, if I were to do a quick ratio test for it as n goes to infinity, okay, this is x to the n over x to the n minus 1. Okay, there is now n in this particular series, and so we have the same interval of convergence from positive to negative 1. Except we need to investigate what happens at the endpoints. So the radius of convergence stays the same. Let's talk about endpoints. Okay. Oh, sorry. Yeah, this has to be equal to 1. And so at negative 1, what happens? Okay. Well, you get this. Oh my. Clean that up a little bit there. Didn't turn out very well. And notice that that's just going to alternate between positive and negative 1. Okay. So we can prove that this diverges by the nth term divergence test. Okay. The limit as n approaches infinity of negative 1 to the n minus 1 does not exist. Okay. It's definitely not 0, and it needs to be 0 for the function to even have a chance of converging. If it's not 0, then that definitively proves divergence. So this diverges by the nth term divergence test at negative 1, whereas the original series did converge. And at the other endpoint, that's just 1 plus 1 plus 1 plus 1 plus 1. That's right. Or another way to put it is as n goes to infinity of 1 to the n minus 1, we get come here. We get not 0, we get 1. And so again, by the nth term divergence test, that series also diverges. So for the derivative, we still have a radius of 1, but the interval of convergence now is open on both ends. And so that's what's going to happen sometimes when you take the derivative. You're going to lose an endpoint of convergence. Okay. And then, as I said earlier, at the bottom of page 622, Dr. Larson has sort of buried what would be a theorem in some other books, that if the derivative converges at the endpoints, then you know for a fact the original function converges at the end. So there we go. That's calculus with power series. You know, probably no surprise that we can derive and integrate. The larger issue is what happens to the convergence as we do so. And as we can see here, both integrating and differentiating have different effects on our convergence. Not so much on the radius of convergence, that stayed pretty consistently at 1, right? The big difference was at the endpoints, and that's what you'll be checking as you go through and do some calculus and talk about the convergence divergence behavior of the resulting power series after you do one of the 2 calculus procedures. So I think that's everything for this weekend. So thank you guys so much for hanging out and watching, and I'll see you in class.